Welcome to the Explainer. Today, we're going to talk about a problem that, well, it's a good problem to have, but it's a massive one. Your app is successful and suddenly everything slows down. That's the database bottleneck. And today, we're not just slapping on a Band-Aid. No, we're going to build a real blueprint for scaling up. And it all starts with understanding the big trade-offs that make or break these huge systems.
So, let's paint a picture. It's a scenario that's kind of ironic, right? It's born from success. Your app is a total hit. Traffic is through the roof. But then things start to get sluggish. Every click, every request, just a little bit slower. And that amazing success you worked so hard for, it's actually threatening to crash the whole thing. So, now what?
So you start digging, right? You're trying to find the source of this slowdown. And almost every single time, all fingers point to one culprit, the database. It's just buckling under the load. And let me tell you, the decisions you make right here, right now, they're absolutely critical. They're what will decide if your app can handle the big leagues or if it just grinds to a complete halt.
Okay, so where do we even begin? Now, the temptation, and we've all felt it, is to just throw more money at the problem. Get a bigger, beefier server. That's called vertical scaling. But here's the thing, that's just a Band-Aid. The real architectural work starts somewhere else entirely. It's not about picking a fancy new technology, it's about looking at the most fundamental thing. How does your app actually use its data? Think about it. Are you handling tons of tiny, quick transactions every second, like a checkout system? That's OLTP. Or are you running these massive, complex queries over huge piles of data for, say, a business report? That's OLAP. See the difference? That access pattern, it is everything.
And that leads us to what is, honestly, the single most important rule in all of database design. Seriously, if you take away just one thing from this, let it be this. Let your queries define your schema. In other words, how your app needs to read the data should completely dictate how you store the data. It seems so simple, right? But that one idea, that is the fork in the road. Every other big decision we're going to make flows from this.
Okay, so if we follow that rule, schema follows query, it immediately forces our hand. We have to make a big choice. Is our number one priority absolute rock-solid data integrity for those OLTP workloads? If yes, that's going to push us right down the path of SQL and something called normalization. Or is our main goal just blazing fast read speeds, maybe for serving up a user's feed, even if it means we have to duplicate some data? Well, that points us straight towards NoSQL and denormalization.
All right, let's make this real. A classic SQL database. Think of something like a payment system. It is all about integrity. You've got data split up into neat little tables. Transactions here, users there, accounts over here. This whole process is called normalization. And the main goal? Get rid of redundant data. So if a user changes their email, you only have to update it in one single spot. This is absolutely perfect for systems that need what we call ACID transactions. It just guarantees that when you do something, like transfer money, it's all or nothing. It either completes perfectly or it fails completely, leaving no messy, inconsistent data behind.
Now, a NoSQL approach, it does the exact opposite. Totally different philosophy. Let's say you're building a social media feed. What matters most? Read speed. You need to get that content on the screen fast. So you denormalize. You basically cram everything you need, the post, the author's name, all the comments, into one big document. And yeah, you're right, the author's name is now copied in every single post they've ever made, but that trade-off is totally worth it because the app can now fetch everything it needs to show that feed in one single super fast read operation. Okay, so you've done your homework, you've analyzed your queries, you've picked your data model, SQL or NoSQL. Things are running smoothly, but your app just keeps growing, and pretty soon you slam into a new wall, a hard one, the physical limits of a single machine. Doesn't matter how much you paid for it or how powerful it is. At the end of the day, one server can only do so much.
And again, the answer isn't just to buy a bigger, even more expensive machine. That's just more vertical scaling, and you'll hit a limit eventually. The real, sustainable, long-term solution is to get more machines. This is horizontal scaling, and in the database world, we have a special name for it, sharding. We're literally taking our data and splitting it up across a bunch of different databases. We might do it based on a range of values or using a hash. There are a few strategies. But the point is, now we can scale out just by adding more servers to the pool.
But, and this is a big but, sharding is not a magic bullet. It's not something you just flip a switch on. It is incredibly powerful, yes, but it's also really complex. To do it right, you need a solid game plan, a playbook. And that playbook starts with what is, without a doubt, the most critical decision you will make in this whole process. And that decision is the shard key. The shard key is everything. It's the piece of data. It could be a user ID, a customer ID, whatever, that the system looks at to decide, okay, which physical server does this piece of data belong on? If you nail this choice, your system scales like a dream. But if you get it wrong, oh boy, you will create bottlenecks that are so much worse than the one you started with.
And the difference between a good one and a bad one is just night and day. A good shard key, something like a user ID, has what we call high cardinality. That just means there are tons of unique values. It naturally spreads the data out nice and evenly across all your servers. A bad key, though, like a sequential ID or a timestamp, it does the exact opposite. Think about it. Every new user, every new order, they all get sent to the very same server. This creates a hot partition, basically a traffic jam on one machine, while all your other servers are just sitting around bored and doing nothing.
Okay, so you've sharded your data. Great. But what happens down the road when you need to add even more servers to handle more traffic? You can't just stop everything and reshuffle all the data. That would be a huge outage. This is where a really clever idea called consistent hashing comes into play. It's mathematically elegant. Just imagine a circle, like a clock face. You place your servers on this circle, and you place your data keys on it too. To figure out where a piece of data belongs, you just start at its position on the circle and walk clockwise until you hit a server. That's its home. Now here's the magic. When you add or remove a server, only its immediate neighbors on the circle are affected. You only have to move a tiny fraction of the data. This insight was an absolute game changer for early distributed systems, like the ones at Amazon.
Of course, there's no such thing as a free lunch, right? Sharding is no exception. It solves that huge single server bottleneck, but it opens up a whole new can of worms, distributed system problems. Trying to join data that lives on two different physical servers, that's super slow and complicated. We already talked about how a bad shard key creates those awful hotspots. And then there's just the basic challenge of keeping your data safe. You have to replicate it, right? But that introduces new headaches, like replication lag, where your backup servers, the followers, fall a little bit behind the main one, the leader.
So that brings up a good question. How do you handle a transaction that spans multiple services? You can't just use a traditional database transaction that locks everything up. It just doesn't work in a distributed world. Instead, we use clever patterns like sagas. The classic example is booking a trip. Think about it. You book a flight. That's one transaction. Then you book a hotel. That's another transaction. Then you rent a car, a third transaction. Now what happens if the car rental fails? Well, the saga pattern kicks in and runs compensating transactions to automatically cancel the hotel and the flight, basically undoing the whole thing. And here's a key detail. Each of these steps has to be idempotent. That's a fancy word that just means you can run it over and over, and you'll still get the same result. That's super important to prevent weird errors if you have to retry a step.
Okay, that was a lot of theory, I know, but it's the foundation for everything. So now, let's pull all these ideas together into a clear, actionable blueprint that you can actually use when you're designing your own systems.
So here it is, the whole journey laid out as a decision tree. And look where it starts. Step 1, always. Analyze your query patterns. That tells you what to do for step 2. Choose your data model, SQL or NoSQL. Then, inevitably, you'll hit a scaling limit, which leads to step 4, implement sharding. After that comes the most important part of sharding, step 5, select that all-important shard key. And finally, step 6, you manage all the new distributed complexity with patterns like sagas. See how it all connects? And since we're talking practical, here is a super important 5-step playbook for how to actually migrate from a single database to a sharded one without taking your site down. This is the zero downtime recipe. First, you set up dual writes, so your application is writing to both the old and the new database. At the same time, you start a backfill job to copy all the old historical data over. A great way to do this is with a change data capture or CDC pipeline. Next, you run checks to make sure the data in both places is perfectly consistent. Once you're 100% confident, you flip the switch and move all the reads over to the new system. And only then, after everything has been running smoothly for a while, do you finally turn off the old database.
You know, at the end of the day, there is no single best database architecture. There just isn't. Every single decision is a trade-off. It's like the famous CAP theorem tells us. In a distributed system, you're always playing this balancing act between consistency, availability, and partition tolerance. You can't have perfect everything. So you're going to prioritize the rock-solid consistency of a bank, or are you going to go for the massive, always-on availability of a social network? The blueprint we've walked through today, it doesn't give you the answer, but it gives you the framework to make that choice with your eyes open. So the only question left for you is what trade-offs are you going to make for your next system?